Well, good afternoon, ladies and gentlemen. Welcome to yet another session for control engineering. I would like to apologize that we haven't met in quite a while. However, we know that we have covered most of the work that we needed to cover from the course outline. So what I need to cover is just a small section of the controller design using state space analysis. If you remember, we were speaking about observability and controllability of a system in the previous class before we took that long break. And we determined how one can obtain or one can test for controllability and observability. For those who have forgotten, I'm just like sort of doing a recap to remind those who have forgotten, and maybe as we wait for others to join before I do what I want to do today. Controllability basically, and I hope you have been in touch with your notes, is the fact that you are able to, if the fact that there exists some control signals within your system that allows that system to reach any state in a finite amount of time. So in fact, if you read some books, another word for controllability is reachability. Reachability. Are you able to use certain control signals within your system to ensure that you can reach any state in a finite amount of time? And that was controllability. So observability, on the other hand, is the fact that there exists some critical states that can be known from the system outputs. Okay, you don't have to know every state in a system, but the critical ones need to be known. So for example, if you remember, we were talking about state variables. We pick only those state variables that are critical for the system. We don't pick every state variable. So in that, using that analogy, we can also say that observability is just the ability that all critical states can be known from a system using the system outputs. In fact, it is not possible to know every state. It's not practical to know every state that exists in a system. But if you know the critical states, then that is termed observability. While controllability is that you are able to reach any state within a finite amount of time. Anyway, there were two methods for determining controllability and observability, and I hope you have done those. Now, if you go to the industry, it doesn't mean that you have to apply all these systems. Some of these systems don't apply in certain areas, but in certain applications out there, they do apply. So it's always just critical to know how to test for controllability and also how to test for observability. Now, because I see we are about 38, I see a hand, Lumasai. Is it by mistake or you want to say something? Okay, silence means maybe he has withdrawn the hand, so we'll just proceed. So what I want us to discuss today, allow me to just quickly share my screen. I forgot to do that. Good. So what I want us to do today, perhaps because it's just a 1-hour class, I might not be able to complete it, but because it's a very critical aspect of control systems design, I will do as much as I can today. If I don't complete it, then we'll complete it on Tuesday next week, because on Monday I'm administering a CAT for a different class, so I'll not be able to have the morning class during that time because the CAT will be ongoing. So basically what I want to do, and this is also part of what exists in your notes, I might use different notations, some terminologies might change, but by now you should understand that you should be able to use different notations or understand different terminologies based on different authors. So I might not follow exactly what exists in your notes, but it is important that you follow what I want to discuss today. It's very, very critical. So the idea here is there is the pole placement method. And this is a method that we use to design control systems using state space model. Now, the fact that there exists a pole placement method, it means there are other methods that can be used. However, those methods are not critical in our case today. The one that I will focus on is the pole placement method. It's the one that's critical. Please allow me to take you back, because we discussed a bit of this when we were doing root locus design. We say that typically, and this is just on the by us. I just thought about it right now, so it's not it's important, but it's just to remind you. Typically, we said that we have a control system. Let's say we have a feedback control system like that. Okay. So we have a plant here. Let me call it P of S, and I'll call this C of S. Now, we have said that it's usually very difficult to keep opening up your plant and changing the parameters of the plant in order to affect the overall performance of your system. So therefore, it has become easier for engineers and designers to leave the plant alone, because once it's installed and fixed, it's always difficult to keep opening it up for tuning. So it has always been that we have a controller that's connected to the plant. So if we want to change the system performance or we want to change we want to tune our system to perform in a different way, then instead of opening up the plant, we can actually tweak the parameters of the controller. And by doing that, we generally also change the parameters of the plant, because the controller could either be just a transfer function or it could be a gain. So we can play around with the gain K, or we play around with the transfer function. And you know, the transfer function has the poles and the zeros. So it's just zeros over poles, okay? That's your transfer function. So typically, we can either decide to play around with the gain of the system or with the zeros and poles of the system, so that we change the dynamics or the system performance of your plants. So in design, the focus has been on the controller design, not on the plant design. Because once the plant has been designed and installed, it is always difficult to keep opening it up and changing its parameters. So what I wanted to mention before I begin is that in all design concepts that we have in control engineering, the design is always focused on the controller. So we change the parameters of the controller to suit a certain performance specifications. And by doing that, we change the performance of the plant. Okay, so that is critical. I mentioned this during when we were doing design using root locus, but this time round we want to use state space analysis. Okay. Now, again, having mentioned that, so please remember that even the concept, that's why we say it's a concept of pole placement, but not for the plant, it's for the controller, because by effecting changes on the controller, we then affect the performance, or we change the performance of the plant. Now, let us look at the model itself. This we have done. I'm just doing a quick recap to remind us, because we'll need this. We had said that we have two equations that represent any state space model. And those equations are AX plus BU. Okay, the notations might be different, but it's the same thing. Y equals to CX plus DU. Remember, we had said lowercase are vectors and uppercase because some books will use bold letters. For us, it's not possible. So uppercase just represent matrices. Okay. Now, if we also remember correctly, we had said that the matrix A is the state matrix. Very important. We'll see why in a short while. Matrix B, we said, is the input matrix. Okay, we defined this when we were starting our discussion on this state space representation concept. Then this is the output matrix. Matrix C is the output matrix. And matrix D is the, let me remember, we called it a feed forward. Some books call it feed forward or direct transmission. Direct transmission. Please correct me if I'm wrong. Direct transmission matrix. Okay. Again, remember that X here, this is the state vector, meaning it's the vector that consists of the state variables. X is the vector that consists of the state variables. U is the input vector. And of course, Y is the output. And the output can be a single variable or it could also be a vector. But in most cases, the output is just one because we're dealing with a single input, single output system. Now, of course, you know the derivative of X, so I don't need to define that. If you remember these concepts, because we discussed them in the initial class that we had, I want us to focus especially on the first one, which is our first equation, which is the critical one, the point of discussion, which is AX plus BU, because the second one is simply talking about the output of the system. Now, let's pay attention to this equation here. Remember, we were calling this the state equation. And we were calling this the output equation. So in design, we don't design the output. So the output equation is not important in controller design here. What is important is the state equation. That is where we focus our attention. And so that's what I have written down here. Now, please remember that this first part of the equation, this one here, is responsible for capturing the dynamics of the system. So here, this captures the dynamics of the system. Okay, the other part, which is the second part of the state equation, is responsible for just how the system responds to inputs, how the system responds to inputs. So basically, whenever you write a state equation, it consists of the matrix A, which basically captures the dynamics of the system. That is how the system transfers its energy from the input to the output and so on. But when you want to just see how the system responds to inputs, then that information is usually captured in the second part of the state equation with matrix B. Okay, remember matrix B is the input matrix and matrix A is the state matrix. Okay, now why are we focused on the state equation? Especially, in fact, in controller design, when we are using state space representation, our focus is on the matrix A. So matrix A is very unique. And I'll give you reasons why. For any controller to change system dynamics, let me just say, Here, a controller has to modify. A controller has to modify the matrix A to change system dynamics. And that is a very critical point, because it means it is the metrics that we must put our focus in whenever we are doing a design using state space representation. Why? Because remember, in general, we are doing a controller design. We are changing the parameters of the controller, not the plant. So in order to change the matrix A, then you are actually modifying the dynamics of the system. It is that matrix that captures the dynamics of the system. So if you modify it, that is how you change the entire system. In fact, if you get the eigenvalues, you've done this in maths, if you take the eigenvalues of matrix A, so you obtain all the eigenvalues of matrix A, those ones are the poles of the system. They become the poles of the system. And why are the system poles important? By now, we all know that the poles of any system are important because the location of the poles dictates system stability. Okay? The location of the poles dictates stability. So if the poles lie on the left half plane, then the system is stable. If the poles move to the right half plane, then the system is unstable. And how do you obtain the poles of the system? By getting the eigenvalues of the state matrix A. That's why the matrix A is very important. And by moving the poles, when we move the poles, the system stability, designing system stability. So it means, therefore, that if we play around with the location of the poles, then we are actually defining the stability of the system. Either the system will become unstable or stable, or even marginally stable. Okay? So therefore, it is important for us in design, because remember, our title is the concept of pole placement. So in general, we are actually saying the concept of designing the matrix A to ensure that the system is stable. Because that's the essence of design. You build a system that meets a certain performance criteria. The most important performance criteria that we have in control systems is stability. That's the most important one. Then you look at transient response later, where you want to know the rise type, the peak time, steady state error. But the most important performance parameter is the stability. Okay. So now, with having said that, please remember that it is in the matrix A that we capture the dynamics of the system. So it is by modifying or by designing an appropriate matrix A that we actually change the dynamics of your control system. And that is how we obtain the stability of the system. Mathematically, ladies and gentlemen, if I wanted to obtain the stability, to obtain the characteristic equation of a system, then you use the formula SI. I is an identity matrix. And then you get the determinant and you equate to 0. I'll come back to that later. Okay? But if you read your books, you probably have already, or the notes that I gave you, you probably have seen this formula here. This is known as the characteristic equation. Remember, in root locus, we also had the characteristic equation. But in state space representation, the characteristic equation is obtained by this formula, SI minus A, and you get the determinant and you equate it to 0. We used this technique also when we were determining observability and controllability. of a system. Now, let me go back to the real gist. And I said if I don't complete it, then we'll do it in the next class. Now, please remember our two equations. X equals to AX plus BU. That's the state equation. And we have Y equals to CX plus DU. That's the output equation. Now, using these equations, can we come up with a block diagram? Again, very important. A block diagram for state space modeling. A block diagram for state space modeling. Using these two equations, because these two equations, that is the state space equation, I mean the state equations and the output equation is what represents the entire system. So let us see if we can come up with the block diagram, because that is important in our design. I'll tell you why. Now, let's start. We want to have, remember, U is an input. A and B are, A is the state matrix and B is the input matrix. So let's start with the first one. If I wanted to draw the first one, I would have, it is AX. So I can start by coming up and X equals to AX. So we can have something like this. So let's say this is our X derivative. That's our X derivative. For me to obtain X, then I have to integrate the derivative. So to get X, so now for me to move from the derivative of X, I'm trying to see how I can move from the derivative of X to X. It means I must have an integrator in between there. So I can put a block here which represents an integrator. An integrator could also just be a matrix, because remember, we are simply manipulating vectors and matrices. So the integrator can be represented by a matrix itself, but we're just putting it there to indicate that it is an integrator. So once we integrate that, of course, the output would be X. Remember, we are looking for X derivative to be equal to AX plus BU, okay? Now, I want to use a feedback system. So if I took a feedback system here and I put A there and I put this here and I make this minus, that's a feedback system, okay? But therefore, if we look at this system in itself, we are going to have, if we have it like this, it's going to be this system on its own. This is where I need you to pay attention for how we come up with this, because you'll see it in your notes and you probably don't understand how it is drawn. Now, here we can say that if I wanted to obtain this, you can see that you have X bar equals to minus AX. But you see, I'm looking for X derivative should be equal to AX. So I can make this positive. If I make this positive here, then now this becomes X derivative equals to AX. But I also need to add BU. U is the input, okay? And it's multiplied by a matrix B. So therefore, at the input, I can decide to have a matrix B here. Then I add it here, and of course, this becomes U. So now you can see from this, we have obtained the first equation, the state equation. Because then if you were to write, remember now this is positive and this is also positive. So if you were to write the equation for the derivative of X, you can see from the equation here, on the right-hand side, we are going to have AX. And then on the left-hand side, we are going to have BU added there, BU added. So that is how we come up with the first part of the equation. But remember, this equation is a model for state space representation. So we have to combine the output equation as well, so that you have input on one end and the output on the other end. So let's see how we can include the second equation. The second equation is y equals to cx plus du. Remember, x is already here. We already have x here. So, but we have cx. So what I can do is I can add c. So that is already cx. And then we need to have du. U is already an input. Du is an input here. So what I can do is I can tap u and I multiply it with d. And once I multiply it with d, I sum them up together here. The arrows are very important. This is a summation, this is a summation, and we sum that, and then we have y. Because clearly you can now see that we'll have the second equation as y equals to, the left-hand side gives you the cx, okay? Plus, from the input, we tap and bring du. So it means we have obtained both equations. In fact, let me just write it now properly here using a different marker, that you can see from here that our x bar or x derivative is now equal to ax plus bu, which was the state equation, and our y here is the same as cx plus du. So this is the block diagram that represents the state space. In fact, you'll see this a lot, and I think it's also in your notes. So that is how you come up with a block diagram. You should be able to draw block diagrams, and you should practice it by looking at different equations, and you see how you can come up with the block diagrams using control notations. But please make sure that the arrows point in the right direction. So you can actually see that the output here is not a feedback, but a feed forward. We are not feeding back the system. Okay, so let's move on. I want to introduce the concept of pole placement. The concept of pole placement, because it is that concept of pole placement that will allow us to change the parameters of our system the way we want to meet desired specifications. So let's pay attention to this. I want to introduce, let me use a different marker. I want to introduce something here that's very critical. And this is what brings out the pole placement design. If I tap the X here, if I tap this X here, and I add some gain K. In fact, let me just say it's always represented as a negative gain. And then I feed that back to my U. So feed it back to U here, like that. What happens is, if I ask now from the equation that I've written in red, what is U? What is U? U would be equal to, using the feedback system that I've provided here, this one. We have tapped from X. So U would be equal to minus KX. Just from the system that I've indicated in red. U, which is the input here, should be equal to minus KX. Remember, X are the state variables. X is actually the state vector. It's the vector that consists of the state variables. So this equation that we have described here as U equals to minus KX is typically called the control law. That is the control law. It is the law that if we solve, then it helps us design any type of control system using state space analysis. So What we can do is use the control law and incorporate it in our state space representation. If we incorporate the control law in our state space representation, then we are able to look for methods of solving the unknowns or solving for the state equations. Then we'll have done basically our design. Okay? Remember, here we are talking about pole placement. But we have said that for you to have poles, you need to get all the poles are obtained from the matrix A. The matrix A, if you get the eigenvalues, those gives you the poles of the system. So notice that it is at this point that I have tapped into I've fed back this system here to a negative gain. Okay, negative gain. It's just a design method, and then we feed it back to the input and we come up with the control law. So when we come up with the control law, something interesting happens. Let's go back to our equations and use this control law. The equations are the derivative of x equal to ax plus bu. Notice I'm now focused only on the state equation, not on the output equation, because it is the state equation that has the matrix A, and it is the matrix A that determines the dynamics of the system. So if we are doing any design, then we are only interested in the state equation that contains the matrix A. But now we have indicated that U itself equals to minus kx. This has been obtained from the control law. Okay? So therefore, if we substitute for U in the first equation, if we substitute, we are going to have the derivative of x should be equal to ax plus. I want to do it the long way for those who might have a challenge. So minus kx. Okay, and so if you solve this, you will see that we have ax. If we solve this, then we now have ax minus bkx, actually, which is just the same as indicating as a minus bk into x. Now, observe very carefully. Let's compare 1 and 2. Let's compare 1 and 2. You will notice that the difference between equation 1 and equation 2 is the coefficient of x. The coefficient of x changes because initially in equation 1, the coefficient of the state vector was just a. But in equation 2, that has been transformed now into a minus bk. A minus bk. Okay? So this transformation is what we use in design. Okay? So the characteristic equation, remember the characteristic equation for this system, the first one, the characteristic equation for this first system is given by, like I told you, Si minus A. You obtain the determinant and equate to 0. Okay? Now, you know S. S is the complex number. Okay? I is the identity matrix. And of course, A is the state matrix. Okay? So now, because we have changed our matrix from A to A minus BK, there's a transformation because of introducing this feedback here, the one in red. So because we introduced the control law, our state equation has changed from equation 1 to equation 2. And because the state equation has changed from equation 1 to equation 2, then the matrix A is also transformed from matrix A to matrix A minus BK. Now, the characteristic equation, when you're using equation 1, is this. This is for equation 1. But the characteristic equation has to transform also when we are using the second equation, equation number 2. And that changes now because we have to substitute for A is now A minus BK. So we'll have SI minus A minus BK. And we equate that to 0. What does that become? That simply becomes SI minus A plus BK. And we equate that to 0. So please note, these are very, very critical points here. Our original state equation is equation 1. However, when we apply the control law to our system, then that state equation is now transformed into equation 2. Now, when it is transformed into equation 2, then what happens, therefore, is that the characteristic equation transforms as well from the original SI minus A equals to 0 into SI minus A plus BK equals to 0. So if you read a lot of your books that deal with the design of control systems using state space analysis, specifically using the pole placement concept, then you will see this equation being utilized. Okay? Now, this is the new, let me just call it the new characteristic equation. So if you have this new characteristic equation and you're able to solve it, then you will have achieved a certain aspect of design because we have incorporated the control law. Okay? Now, there are about 3 methods that can be used to solve this. Okay? If you want to solve this, because then you'll be given a problem, you'll be given a typical problem. In that problem, maybe you're given a state equation. So you already have the state matrix, you'll have the input matrix as well. You might even be given the gain K, and then you're required to design a new system based to meet a certain specification. So that basically means you need to solve for this problem here. And if you're able to solve for this problem, then you'll have met those design specifications. Now, to solve this, we have 3 main methods. The first method that is used to solve the new characteristic equation that incorporates the control law is called the matching coefficient. So some books might have solved their problems using a matching coefficient method. It's a very straightforward method, okay? You can also solve this using the Ackermann's method. Ackermann's method. It's not Ackermann, the outlet, the clothing outlet. It's Ackermann, the inventor of that method of solving the control law. And of course, the third one is known as the transformation, which is what we'll focus on, the transformation method. So typically, you'll receive a problem that requires you to do design. There's one problem already in your notes that is solved. I want you to figure out if that method is the matching coefficient method, the Ackermann's method, or the transformation method. However, I am going to provide in the next class a problem, and I will solve it using the matching coefficient method. We see its solution, then use the Ackermann's method for the same problem, see its solution, and then lastly, use the transformation method and then see the solution. Then we are able to compare the solutions for these 3 different methods so that we can quickly draw conclusions as to what method you can easily use, because unless you're specifically asked, which is never the case, that you'll be asked to use a specific method to solve a problem. Because this is a design problem, we don't restrict you on the method to use. We allow you to pick whichever method is convenient for you, because what is provided in control problems is you're given the state of the system as it is currently, then you are provided with the desired specifications for that system, and then now you're asked to carry out the design so that you meet the desired specifications as provided. So we never restrict you on the method or on the technique that you use. We only expect that you meet the desired specifications as provided for your system. So it is very, very important, ladies and gentlemen, to take time before I go into the solution of a problem, to go back and look at how, one, our state vector, or not the state vector, but how our state matrix is a very, very important matrix in determining the dynamics of your system, and how we can use it, because it is the unique matrix that allows us to obtain the poles of the system. And once we have the poles of the system, we can determine, or we can decide on the stability of our system. We can play around with the stability of the system, knowing the eigenvalues of the state matrix. And then, of course, you know that I drew the block diagram to introduce the concept of the control law, so that when we apply the control law into our original state equation, then we come up with an equation, a characteristic equation that needs to be solved. So this characteristic equation can be solved using 3 different methods, and then you see the solution that arises from there. So again, please don't forget how, because this goes hand in hand with controllability and also with observability. You must be able to figure out in your design, and we'll do that once you have completed the design. So you've given a problem, you've been told the current state or the current dynamics of your feedback system or your plant, then you're asked to design a system that meets a certain specification. You're given the desired specifications. You decide on the pole placement method, but then you solve it using any one of the 3 techniques that I've provided here. But in that solution, you always have to check for observability and controllability. Because if you make a mistake of designing a system, then you don't test for its observability and controllability, then your system might again bring issues along the line. So once you do your design, you have to test. That's why I started this unit by teaching you how to test for observability and also how to test for controllability. So once you make your new design, so once we have obtained a solution here, we need to test for both controllability and observability, because we agreed that all our systems must be observable and must also be controllable. Very, very important in control systems, that your systems are observable and they are also controllable. Like I stated, I said controllability is also called reachability. It simply means that you have certain sets of control signals that allows your system to reach any state within a finite amount of time. That is very critical. It's like when you're driving a car, for example, and I blindfold you. The system, the car can still be controllable even if you are blindfolded. Why? Because you still have a steering wheel and you know the location of the gear. So, or just the fact that you have the steering wheel, you can still be able to a certain degree control the car if you're blindfolded, because you're using the steering wheel, meaning you still have a set of control signals that allows you to reach a certain state, and that state could be distance. You're moving from a certain position to another, or it could be another state could be, and I'm mentioning state variables now. It could be position displacement, or it could be velocity, or even it could be acceleration. So your system is still controllable. Even if you are blindfolded, you can still accelerate your car, you can still move at a certain speed, and you can still move from position A to position B. That means your system is controllable. Then observability, we said, is the fact that you are able to know all the critical states from the set of outputs that are available, okay? So it is not practical, though, to know every possible state. Like I said, if you're driving a car, for example, there are certain states in the car that exist but are not important. If you're driving a car, the temperature of the car is not really a very important state. It is a state, but it is not a very important state in determining the performance of that car. You can still drive comfortably when the temperatures vary. So it means that the temperature of the car could still qualify as a state, but it is not a critical state. That's what we mean. So we'll test for this in the example that we'll provide in the next class. Like I've said, for those who joined late, I will not be able to do this class on Monday. I will instead do the class on Tuesday, the next 1 hour class, because I'll be having an exam going on, a CAT going on Monday at 8 a.m. Is there any question? Because our time is almost up and I beg to end it here. Please note that these are the last sets of our class. I'm just trying to finish and explain certain things that you might not understand. Yes, Oshor.
Yes, thanks. Yes, I just had a concern. We've been doing control systems last year in control engineering. So I was wondering if there's a way we could get some kind of feedback regarding the CAT. There's one question I'd love to see how it's the root lock as it's sketched.
So you want your CATs back?
Not necessarily, just some feedback regarding it.
I don't understand. You need feedback in terms of performance or in terms of solving the problem?
Yes, there was one question for sketching the root.
Oh, okay. Okay. So would you like me to explain or provide you the solutions to this CAT?
Yes, the solutions will work, or the explanation too.
Okay, so what then I'll do, because of the time limit that I have and I need to complete this work in the next class, I am going to send through the CR the solutions to the CAT. But give me, because I'm not in the office. I am back, yes, but I'm not in the office. I intend to go there sometime this week, maybe on Friday. So what I'll do is I'll access these, because I solve them by hand. I'll have to access it from the office and then scan it and then send it to your CR so that you're able to see some of those root locus methods. But again, I intended to have us in January, because your exams now, from the timetable that I saw, that your exams would begin, I think, on the 20th. So we still have like about 2 weeks thereabouts in January, where we can actually just take time and focus on revisions. So you bring problems, we solve them, we look at some of the challenges that you already have or you've encountered, and we try and just solve them as we prepare for the exams. So I will provide you with the solutions to the CAT. I have no problem with that at all. Just give me a few days so that I go to the office. I have no access to the office at the moment, but I will send them through your class rep. And then hopefully in the next year, when we get there, if we get there, we'll spend about a week or two just trying to do revisions and solving different problems so that we have a wide perspective of the things that we have been doing, covering the whole semester. I hope that's fine.
Yes, thank you.
All right. Thank you guys so much. Thank you for your time and for your listening. I think we meet again on Tuesday next week. Have a good evening. Bye-bye.